longitudinal redundancy checking is a type of error detection method used in digital transmission. It has two different kinds of parity. One is the odd parity and the even parity. And to better understand that, let us proceed to the example. Consider data strings. Use even and odd parity. So for the even parity, we will put 0 alongside the MSB if the numbers of ones in a data string is even, and 1 if it's odd. Conversely, on odd parity, we will put 0 if the numbers of ones is in odd, and 1 if it's in even. And in this set of data, the first and second data strings are in even. That's why for the even, we will put 0, and for the odd parity, we will put 1. And the third data string, it has an odd numbers of ones. So for the even, we will put 1, and for the odd, we will put 0. Now, let's proceed to the LRC, or the longitudinal redundancy checking. It is also a type of error detection in digital transmission. And unlike VRC, it is a two-dimensional parity check, and the parities are calculated for each column. Consider the ASCII bits of the several characters for uppercase A, lowercase b, s, and d. In the first step, you will get the binary sum whilst ignoring the carry. And after you get the binary sum of these data strings, it is now called as the parity bits. And these parity bits will be put alongside the data strings for the receiver to read it. And take note that the parity bits can be put on the leftmost or on the rightmost depending on the system.
Cyclic Redundancy Check, or CRC, is a reliable and simple error detecting code widely used in digital networks and storage devices to detect accidental data corruption from noise or transmission errors. The primary purpose of Cyclic Redundancy Check, or CRC, is to detect errors in data transmission or storage. It ensures the integrity of data by identifying accidental alterations caused by noise, interference, or other disruptions. We need to find the CRC and transmitted data of the following, given the divisor and the message. But first, we need to find the append number using the formula L-1, and as we solve it, we derive into 3. Solving the problem, we use the XOR truth table and the divisor with the append number on the right side of the message. Then we use the division to derive our answer, 001, as a remainder and CRC. While for the checking, we apply the same method like our first solution to arrive to our final answer, 000. And as we can see, it is our append number.
Checksum is a calculated data set. Example of it is transmitted data to detect errors introduced during the storage or transmission. It is used to ensure the data integrity. So the main purpose of checksum is to ensure the integrity of data during storage or transmission by detecting the errors that may occur. It acts as a efficient and simple error detection mechanism. So here are problem solving checksum, and find the checksum of the given blocks. So we are given our first block and second block. So we will perform a binary addition here, and our addition will result into 1 1 1 0 0 0 1 0. Then we will complement it, and it will result to 0 0 0 1 1 1 0 1. Then after that, to check the transmitted data, so we will result here by adding all the result, the first complement, the first block and second block. So the answer will be 1 1 1 1 1 1 1 1. Parity check is a simpler error detection technique that ensures that once in a binary sequence is either odd or even parity. So the main purpose of parity check is to detect the single bit errors in the data during transmission or storage. It is simpler error detection technique that ensure the data's integrity by verifying the number of ones in binary sequence that matches the expected parity. So for our parity check, we are given a 7-bit data 10110001. So we are tasked to determine the parity bit, and we'll identify it in even and odd parity. So take note that all we need is to identify the ones of binary sequence. And here we can see that 10110001 is a result of a even parity. So for the odd parity, we will indicate a 1 to make it result in a odd parity.